Okay, we're going to continue talking about Samuelson's overlapping generations model and the Gale diagram that we had last time. And the way this worked, we have this feasibility frontier. And we have this offer curve for an agent who has initial endowment, let's say Y when young and Y with old. And we're going to have a structure where endowments and preferences are the same for over young consumption and old consumption for each generation. And the way this worked is we had this machine. We started with an initial condition where we endowed the old people at time one with this amount. From feasibility, we came down here and we cast how much we would then award in a competitive equilibrium to someone with to a young person at time one. This is an old person at time one. But to make that young person at time one content in a competitive equilibrium, we have to give that young person this amount on the offer curve when they are old. We get this amount. And then we could do that and then award, come over to the feasibility line, and then we could give this person, an old person, this amount. When the person is old, we would have to give, we could give them that amount. I misspoke. Let's go this again. I give this, what we found is I would have to give, if I gave the person who was born in one this amount when he was old, he or she is old, I could then give a young person at time t2 this amount. But to make that person happy, I would have to go to this offer curve and get C2 in period. Give the person who was born in 2 this amount when they're 3, when they're old. So the graph goes with the arrows like I said, and if we start with this situation, we eventually converge to the low interest rate equilibrium, steady state. Okay, so that's how this Gale machine works. There's another example that we could do that's kind of fine. We can move in the direction of converting this to a difference equation that we can solve. If we use the special case, exactly the same that we have above, but we're going to have log preferences. So that the margin utility of consumption is just then 1 over C. Then we can get a long way toward getting the offer curve analytically. So the offer curve would be could be written like this if you just do a little calculus. the same endowment pattern. And then CI plus 1I when the person's old is going to be alpha I inverse on CII. And if we read where alpha I is going to be the ratio of marginal utilities, and it's the alpha I is the well, this defines alpha I. So if we use feasibility and rearrange, we'll get this difference equation. It's a nonlinear difference equation. That's going to be a big number. And this is true for I greater than or equal to 2. So we actually start with an initial condition for alpha 1, which is in this graph, alpha 1 would be our initial slope on the offer curve. So for example, it would be, here's our offer curve, it would be that slope. And then we would I'm sorry, it would be not that slope, it would be, now just think about it, it would be the slope of a straight line that connects the point on the offer curve to the endowment point. That's what the slope is. And that reflects that there's going to be a tangency point between an indifference curve there. So think about that. So that's how we get this difference equation that we could solve. And if you solve this difference equation with this example, you will see that it's converging to the lower fixed point. We'll come back and we'll solve in difference equations like this soon. So that's how the Gale machine works. I've been inarticulate in explaining it, but if you read either Gale's paper or the machinery in chapter 9, chapter 10, you'll be able to do it much easier than I did. Okay, so what we're now going to do is we're going to follow Samuelson and do sequential trading. So in this setting, there's going to be trading at each date, t greater than or equal to 1. So here's the way this is going to work. The endowment pattern, we'll make the endowment pattern YT T plus 1 in terms of goods. That's going to be, we'll make it to facilitate the existence of a stationary equilibrium. You're going to have some endowment Y when you're young and some when you're old, and we're going to make Y young greater than Y old. And this is going to be for all t greater than or equal to 1. And we'll endow the initial old with this amount too. T equals 1. Okay, in addition, we give the initial old, this is Samuelson's idea, per capita m units of an inconvertible we'll call it paper currency. It's not a commodity. It's intrinsically worthless. It's intrinsically worthless. It is in nobody's utility function. And it's denominated in dollars or pounds or euros or yuan. Okay. And we're going to let it's intrinsically worthless, but it might have value under certain circumstances. So this is the supply, and it's in the hands of the old. In hands of initial old. And then we're going to allow people to trade it. People can trade it. And I'm going to write down the budget constraints of the young agent born at time I. So an agent named I has a budget constraints that looks like this. When it's young, it can buy consumption, and it can also acquire money, these dollars, on these terms. It can take some of its endowment, YI, and it can allocate it partly to consumption, but it can actually save now in the form of this unbacked currency. And the way it gets the unbacked currency is from, it's a young person, it purchases, it exchanges time I goods to generation I minus 1 person at a price PI, where the price of PI is dollars at time I per unit consumption good at time I. It's the price level. So this quantity here, this quantity, that's so-called real balances. It's savings in the form of money, denominated real balances. If I take dollars and I take dollars per time I good, the units of this will be time I good. That's the way this works. Okay, that's the budget constraint at time today when I'm young. And when I'm old, what I get is I sell the money. The price has possibly, the value has possibly changed. So when I'm old, that's my endowment. That's my savings that I've carried over. And we're going to require, this is important, could think of this as no counterfeiting, or I am not permitted to issue money. I have to hold, I can't go short, no short in dollars. Okay, so if I take these two equations, at equality, and eliminate, I'm going to eliminate the MII, and I'm going to substitute. So I'm going to solve the second equation for MII and substitute it into the first equation. I will get this equation. It's going to kind of look nice. So this is a key step. That's our equation. And what you'll notice if you stare at that is if I set, so this is free association, but if I set PI plus 1 over PI, that's the gross rate of inflation. That's the gross rate of inflation in the price level. If I set that equal to AI alpha I, and I set this equal to, what I've done is I've established a, it's an isomorphism and an equivalence between the budget constraint that this person faced in our imaginary Era de Brewer economy with all trading occurring at time 0. I'm now imagining it's occurring sequentially through the medium of exchange called currency. So if we set that as this is equivalent, which is going to mean we've actually know a lot about what Samuelson is going to define as an equilibrium. So let's move to how he defines an equilibrium. So a couple definitions. A nominal price level sequence is it's just a sequence of non-negative. We're going to make it positive always. So a nominal price level sequence is just a sequence of positive numbers. I want to make them positive. And now we can have a definition. An equilibrium with valued, we're going to call it fiat money. So it's inconvertible. So what is it? It's a pair. It's a feasible allocation. It's a feasible allocation. And a nominal price level sequence with PI less than plus infinity for all I, such that given the price level sequence, the allocation solves the consumer maximum problem, constrained maximum problem, constrained maximum problem for all consumers I from time 1 on. That's it. Kind of a remark. PI less than infinity, that implies that 1 over PI is positive, which means that money, fiat money is valued always. That's what that means. And so we're going to say remark if 1 over pt is switching between is greater than 0 always, we call it a monetary equilibrium. It's kind of Samuelson's notation or language. Neil Wallace has used this a lot. You know, if 1 over pt equals 0, I'll be vague. Anytime we call it a non-monetary equilibrium. It's an equilibrium in which money is not valued. So that's our setting for Samuelson's model. Kind of a remark. Another remark is, you know how, we know how to compute an equilibrium. And another remark is, I say remarks, there is a continuum of equilibria. How do I know that? How do I know that? The way I know it is this isomorphism right up here. Once I make this connection, the household's problem, so its choice of allocation, each allocation is identical to what it was when we were studying the equilibrium with time zero trading, and we were using the David Gale machine. So if we have one of those equilibria, we can just interpret alpha I as that we get from this machine. There's a monetary equilibrium embedded in each one of these paths, believe it or not. So all of these equilibria with all these possible paths are consistent with a monetary equilibrium. And with a little cleverness, we can immediately back out the alpha i's. And with a little cleverness, we can also immediately back out the initial price level P1. And we could get it from staring at this graph. We get it from staring at this graph. So I'm going to kind of give this as an exercise. Where is the initial price level hiding? Here. I'll leave that on. Where's the initial price level hiding there?